Good morning. I'm Andrea Linhoff, a systems engineering leader at ULA and your host for live coverage of today's Vulcan launch. I'm joining you from ULA's Advanced Spaceflight Operations Center at Cape Canaveral Space Force Station in Florida. Thanks for getting up early for the second launch of ULA's Vulcan rocket. Today's flight is dubbed CERT-2, signifying the second certification mission for the new Vulcan rocket. The first certification flight successfully lifted off earlier this year. The Vulcan rocket will continue ULA's legacy of support to our U.S. government, civil, and commercial customers. And with today's flight, we'll move a step closer to certifying Vulcan for government missions. We'll learn more about certification throughout the broadcast. On board the Vulcan rocket is an inert payload along with several tests and demonstrations for future Vulcan capability. Liftoff is scheduled for 6 a.m. Eastern at the top of our 3-hour launch window. In addition to watching our webcast, you can also follow live mission progress at ulalaunch.com. About 40 minutes ago, the count entered a 60-minute planned hold. We have 2 planned holds in our launch count, which give our team additional time to resolve any issues prior to entering the terminal count. At this time, the team is not working any issues and we are proceeding towards an on-time liftoff. Live coverage this morning will continue through second main engine cutoff, which occurs at about 35 minutes after liftoff. To kick us off, let's learn more about today's flight from ULA's President and CEO, Tori Bruno.
We are coming up on a very important and exciting launch. This is our second flight of Vulcan, which is also our second certification mission. This is really important to both our company and especially our customers because this flight is necessary for us to begin flying national security space missions. And there are already a pair of these in the pipeline that are vitally important to our country. Our original plan had been to fly Sierra Space's Dream Chaser vehicle, a really cool mission that we have been supporting them in for a number of years now. However, they're just not quite ready in this time frame, and we have to proceed in order to clear the way for national security. Don't worry about Dream Chaser, we will circle back and fly them as soon as they're ready. In the meantime, we will be flying a mass simulator, sometimes called an inert payload, and fly a very similar trajectory to what we flew on CERT-1. Because we have that inert payload, we are also free to add a number of experiments and technology demonstrations that will help us with our enhanced upper stage plans in the future. This will allow us to have more performance, to do more agile trajectories and insertions, especially for our national security space customer, as well as extend the duration of that upper stage, which is essential for a whole number of things that we will do both commercially and to contend with our country's challenges in space that are being presented by adversaries like China, and allow us to provide that kind of support that will keep space a peaceful environment and one in which our country feels secure. So this mission is coming up soon. It's going to be very exciting, and then it opens the door for whole new missions for Vulcan in the future. Thank you.
As we look at the Vulcan rocket on the pad, we see the American flag across the inner stage with the ULA and Vulcan logos on the payload fairing. Though it's hard to see now with the booster filled with cryogenic propellants, the Vulcan logo is also wrapped around the first stage. And a portion of the booster includes spray-on foam insulation or SOFI to improve thermal protection and enhance performance. Let's learn more about this innovative new rocket.
Designed by ULA's engineering team and built by our skilled technicians, the Vulcan rocket, once fully stacked, stands 202 feet and weighs nearly 1.5 million pounds fully fueled. Vulcan's first stage is built using lightweight, machined and bump-pressed orthogrid aluminum panels to form the liquid propellant tanks. Once formed, Tanks are joined together using circumferential friction stir welding before heading to the paint booth. Prior to mating to the booster, the BE-4 engines are individually hot-fired. At the base of the rocket is the Vulcan booster, powered by twin BE-4 engines. For additional thrust at liftoff, solid rocket boosters, or SRBs, are attached to the rocket. Atop the booster is ULA's ultra-thin stainless steel Centaur upper stage, powered by two RL-10C engines. Spacecraft are encapsulated inside a protected 5.4-meter diameter payload fairing. With production complete, the rocket travels from the ULA factory in Alabama to the launch site in Cape Canaveral on ULA's rocket ship. Once in Florida, ULA's launch operations team begins a series of events leading to today's countdown. The process begins by lifting the 109-foot booster onto the newly constructed Vulcan Launch Platform, or VLP. For missions requiring additional thrust at liftoff, SRBs are attached to the side of the booster. Then, following interstage mate, the Centaur upper stage is transported to the VIF and lifted into position. Lastly, the encapsulated payload fairing is lifted and mated to the Vulcan rocket. Once fully assembled, the launch countdown begins, with moving the rocket from the VIF to the pad. Riding atop the VLP, Vulcan's trip to the pad is about 1/3 of a mile. Weighing in at approximately 2 million pounds, the VLP supports the rocket and contains air conditioning, electrical, and commodities lines. Throughout the 20-minute trip, a support van leads the move, followed by the payload van, providing communication with the spacecraft, while the ground van provides support to the rocket. Track mobiles at the rear power the nearly 3 million pound convoy, which also includes an environmental control system, providing air conditioning to the payload and rocket, as well as a backup generator. With the rocket on the pad, the launch team transitions to fueling and other final preparations.
As we approach the terminal count pole, let's check in with Arlena Moses to share today's Space Launch Delta 45 weather forecast.
Thanks, Andrea. We just heard from our lead launch weather officer stating weather is great for our launch this morning. And if we take a look at radar behind us, we can see we've had just enough dry air move in over the past 24 hours that has pushed most of our storms and showers that are happening overnight down to our south. The little bit of activity we have up across to our east over the Atlantic Ocean remains a little too shallow and a little too far to our east to be a concern here over the next couple minutes. Our main area of concern here is within this white ring, which represents 10 nautical miles. So if we go here and take a look at our forecast here, we're going to only be looking at a POV of down to just 5% with no significant launch weather concerns tracking. Winds are going to remain from the east, this light breeze about 10 to 15 knots, with temperatures around 80 degrees this morning. Weather looks great for the launch. And back to you, Andrea.
This is Vulcan Mission Control at T-minus 7 minutes and holding. Launch conductor Dylan Rice has informed the launch director that the launch team will need a few extra minutes to complete preparations. At this time, we will not be resuming the countdown for liftoff at the opening of the window. A new target launch time has not been identified.
LCSYS on 1.
Go ahead.
Step 950, all secondary decoms verified on RF link.
Roger.
This is Vulcan Mission Control at T-minus 7 minutes and holding. You'll frequently see today that there's a VC2S for our configuration that we're flying. The V, the first in this configuration, stands for Vulcan. C, the second, is our Centaur upper stage. 2 indicates the number of solid rocket boosters, so for today that's 2. And then S is standard, and that is our payload fairing length. This is Vulcan Mission Control at T-minus 7 minutes and holding. The Vulcan launch vehicle experienced a data dropout which caused the ground systems to stop propellant flow to the rocket. The team has configured the systems to resume flow, and we are working to establish a new T0 shortly. This is Vulcan Mission Control at T-minus 7 minutes and holding. Building on more than 130 years of combined Atlas and Delta launch experience, ULA's Vulcan rocket introduces a balance of new technologies and innovative features to ensure a reliable and accessible space launch service. Let's hear more about this incredible launch vehicle.
Vulcan Centaur production begins with aluminum sheets, expertly machined to remove more than 2/3 of the weight, resulting in the structurally strong yet lightweight orthogrid panels that form Vulcan's propellant tanks. The panels are then bump pressed to form the curves required to complete the tanks. At the same time, rings, adapters, and other structural components are precision milled. Next, the aluminum domes, panels, and other structures that form Vulcan's propellant tanks are first cleaned and etched to a smooth, even surface, and then anodized to harden and prevent corrosion. Following an ultrasonic inspection, 5 completed panels for the liquid methane tank are assembled and joined together using friction stir welding. Unlike traditional welding, where filler material is used to join components, friction stir welding uses a head to stir the metal of the 2 panels together as it moves down the seam. The resulting joint is stronger and produces a lighter weight, higher performing tank. The process is repeated to create the liquid oxygen, or LOX tank, followed by attaching domes to complete the tanks. Circumferential friction stir welding is then used to join the 2 propellant tanks that comprise the Vulcan booster. As production continues on the booster stage, stretch-forming gore panels for the Centaur second stage propellant tanks is underway. The stainless steel gore panels are welded together to create the propellant tank domes. The gore welder is one of several highly specialized welding stations in the Centaur production process. Just down the aisle, Centaur V's massive intermediate bulkhead is mated to its ultra-thin tank. Once both propellant tanks are welded, they're mated together to create the Centaur V second stage. Before moving to final assembly, the 5.4-meter booster is sprayed with foam insulation, followed by booster mask and paint. Twin BE4 engines are individually hot-fired prior to making their way to the factory. They are then mated to Vulcan's thrust structure and protected by a heat shield. With production complete, Vulcan's first and second stages depart the Decatur factory and make their way to ULA's rocket ship to begin their journey to the launch site. Following the journey to Cape Canaveral, the Vulcan components are offloaded from rocket ship and transported to a vertical integration facility, or VIF, where they are lifted onto a Vulcan launch platform, or VLP. The vehicle then travels to the pad, and the launch team transitions to fueling and other final preparations.
LC, ALC. Go. Contact clock has been reset with a new T0 of 10:30 Zulu. We are currently at L-29 and counting. Roger.
LC, RC. Go. The range has approved our new T0 of 10:30:00 Zulu.
Roger.
This is Vulcan Mission Control at T-minus 7 minutes and holding. A new T0 has been identified at 6:30 a.m. Eastern.
Perform Centaur LO2 fill and drain valve cycle test.
Roger.
Fuel 2, perform Centaur LH2 fill and drain valve cycle test. Fuel 2, yeah, okay. You copy. Fuel 2, LC.
Go ahead.
And I just wanted to ensure you copied the transmission to re-perform the fill and drain valve cycle.
Affirmative.
Roger. Has gas, establish scan patterns 62 and 63.
Roger.
This is Vulcan Mission Control at T-minus 7 minutes and holding. Launching rockets takes the coordination of a team of experts. Let's hear from launch conductor Dylan Rice on what it's like to lead a team on launch day.
I am Dylan Rice, Systems Test Engineer and Launch Conductor for United Launch Alliance. The launch conductor is most visible on launch day. We are overall responsible for execution of the countdown, ensuring that the team is ready to go. Our launch team is divided up into several smaller teams. There's one team that's focused on the booster. There's another team that is focused on the second stage. We have a third team that's focused on the electrical and avionics systems. The primary role of the launch conductor is just to manage all those teams and make sure that everybody is ready when the launch window opens. Launch day starts pretty early in the morning. We're usually getting started about 10 hours prior to launch. There are teams that are out at the launch pad doing the final securing on the launch pad. That might be associated with our propellant storage farms or our environmental control systems. There's a lot of work that goes into just the general preparation, final preparation of the pad for a launch. Once we have the launch pad secured and all of our systems are ready to initiate tanking, we clear the launch pad and we start to transfer propellant from the large storage tanks onto the launch vehicle. We also do things like pressurize our reaction control system. When we load helium on the vehicle, we use helium as a pressurant. All those items are considered hazardous, and we can't do that with people out at the pad. Once the vehicle is loaded and ready, then we perform our final terminal count and launch. There is an aspect to the job that is almost like being the coach of a sports team, and that is when you kind of face challenge after challenge, and you have to ensure that you keep your team in the right mindset to keep their heads in the game. We've had multiple launches. I can think of 3 or 4 off the top of my head that have just been absolutely wild campaigns. There's one in particular. We had a launch window that was in late afternoon in the middle of the summer. We had 4 launch attempts in a row, and the weather just was not cooperating with us. Day after day, the weather pattern was repeating, and we came in day after day and loaded the rocket and tried again and had the rocket ready, and the weather just wasn't going to let us go. At that point, you're almost like a coach reminding the team at halftime. It's like, look, we're not out of this game. We have to keep playing, and eventually we'll prevail, and we did. You know, no matter how many dozens of missions that I've executed, it never gets old. And when we pick up the terminal count, my heart rate definitely goes up. It's exhilarating every time, and it never gets old, and I hope it never gets old because I really love watching it.
This is Vulcan Mission Control at T-minus 7 minutes and holding. ULA builds Atlas and Vulcan rockets in a 1.6 million square foot facility in Decatur, Alabama. Here's a look inside.
Successfully launching missions to every planet in the solar system, in addition to critical national security, science, weather, and communication satellites, ULA has established a long-standing industry reputation for reliability and orbit accuracy. While our rockets lift off from launch pads in Florida and California, the journey to space begins in Decatur, Alabama. At approximately 1.6 million square feet, ULA's production facility is an always-on workhorse where technicians simultaneously build components for Atlas V, Delta IV Heavy, and Vulcan Centaur rockets. Booster production begins when large aluminum plate stock is loaded into one of 4 double gantry skin milling machines, where aluminum is milled into patterns designed for building tanks and other components. This process helps reduce the original weight of each panel by 70%, while maintaining approximately 75% of the original material strength. After machining, skin panels are transported to the brake form and bump pressed into the precise curved radius required to create fuel tank barrel sections. Components made from aluminum require anodization to protect from corrosion. For this requirement, certain components, like skin panels, are first given a high-pressure wash and then dipped in a series of chemicals to complete the sealing process. Skin panels are then transported to the vertical friction stir welder, where they are lifted and forged together to form the barrel sections of the fuel and oxidizer tanks. Delta IV and Vulcan Centaur tanks are comprised of 5 skin panels, while 4 skin panels form the Atlas V tanks. Friction stir welding is a unique process accomplished by a pin tool, which applies frictional heat and stirring of the parent material to form a weld. This process only uses friction as the heat source and has no filler material, making an extremely strong welded joint. Completed aluminum barrel sections then move to the circumferential friction stir welder, where domes are welded to each end, completing the first stage fuel tanks. After pressure testing, which verifies the integrity of the welds, the next stop for booster fuel tanks is the spray-on foam insulation booth, or SOFI. This is where completed tanks are primed, then insulated to protect from the acoustics that occur at liftoff. Tanks then move to final assembly, where components like wiring and engines are added. In addition to the first stage, or booster stage, ULA's second stages are also built in Decatur. The factory has recently undergone a major reconfiguration, resulting in a new state-of-the-art Centaur V production line to increase the speed at which Vulcan Centaur second stages are built, assembled, and tested. The Centaur upper stages for Atlas and Vulcan are built using a thin stainless steel structure, making it the most efficient upper stage currently in use. To create the domes or bulkheads for Centaur's 2 tanks, gores or pie-shaped sheets are welded together. The bulkheads and tank skins are then assembled using a combination of spot and seam welds. Spray-on foam insulation, or SOFI, is then applied to the Centaur tank to provide thermal protection for the cryogenic fuels. Centaur's tanks are known as pressure-stabilized tanks because 90% of their weight and structure at launch is from the mass of the fuel and oxidizer loaded prior to liftoff. The Centaur tank then moves to final assembly, where engines, avionics, pneumatic, and propulsion systems are installed. At the end of the production journey, all systems on both the booster and Centaur are fully tested, and the stages are prepared for transport to the launch site. With testing and transport preparations completed, Atlas V, Delta IV Heavy, and Vulcan Centaur rockets exit the factory and roll about a mile down the road to a dock on the Tennessee River. Once loaded onto the RS rocket ship, ULA's specially designed cargo boat, the rockets begin the 8-day trip to Cape Canaveral Space Force Station, Florida, or the 23-day trip to Vandenberg Space Force Base, California.
LC prop 1.
Go.
SGI charge to flight pressure.
Roger.
L minus 16 minutes.
This is Vulcan Mission Control at T-minus 7 minutes and holding. Earlier this week, the ULA team conducted an extensive practice ahead of today's launch attempt. We're looking at video of the wet dress rehearsal. The WDR is a full day of launch test. During the WDR, Vulcan's booster and Centaur stages are powered up. Avionics are tested and final preps to the ground systems are accomplished. Next, the rocket is loaded with methane, liquid oxygen, and liquid hydrogen. With the rocket fueled, the team proceeds into the terminal count, which includes pressurizing the rocket, arming various systems, and transitioning the rocket to internal power. The WDR count ends just seconds prior to T0. The rocket is then safed, the cryogenic propellants are drained.
PNE-1, initiate post-liftoff launch head umbilical purge autofile.
Roger.
L minus 14 minutes.
Top 1, perform GNG snuffer purge cycle test.
Roger.
LT, OSM1.
Go.
First step, 1040, launch sequencer overrides established.
Roger.
LC, PNE2.
Go.
CUC airborne pre-chill is complete, recorded time 10:16:13, Zulu.
Recording 10:16:13, Zulu.
Good copy.
L minus 13 minutes.
Flight control, perform launch on time verification.
Roger.
OSM, place SRB ignition SNA switch in the enable position.
SRB ignition enabled.
Verify the FCO, ROC, and OSM hold fire switches are in the proceed position.
Ready to proceed.
RC, verify solar radiation acceptable for launch.
Verified.
PNE-1, verify post-liftoff launch head umbilical purges configured for launch.
Verified.
LC prop 1.
Go.
GNG snapper purge cycle test complete.
Roger.
LC flight control.
Go.
Launch on time verified.
Roger.
L minus 12 minutes.
RLM, verify red line monitor and event table in the correct configuration for terminal count.
Verified.
LC LOX 2.
Go.
Centaur LO2 at flight level.
Roger.
LC fuel 2.
Go.
Centaur LH2 at flight level.
Roger. Terminal count briefing. If a condition exceeds a launch constraint anytime after the terminal count status check, the observer shall announce hold, hold, hold on channel 1, identify their station, and briefly state the reason for the hold.
All communications switch to channel 1. All personnel and visitors remain in present position until launch. Maintain operational silence in the LCC.
All steps complete prior to the status check. LC switch ready.
We remain in the hold as we continue towards liftoff. In a few moments, launch conductor Dylan Rice will pull the launch team for the final go to pick up the count. 29 engineers and managers are pulled for system status and readiness to proceed. This is the final status check for all Vulcan vehicle systems, ground systems, and the U.S. Space Force Eastern Range. The vehicle system readiness poll includes electrical systems, hydraulics, pneumatics, propulsion systems, flight control, and propellants. Let's listen in as Dylan Rice performs the final polling.
All minus 10 minutes.
Status check to proceed with terminal count, Vulcan systems, propulsion.
Go.
Hydraulics.
Go.
Pneumatics. Go. LNG.
Go.
LO2.
Go.
Water.
Go.
Centaur systems, propulsion.
Go.
Pneumatics.
Go.
LO2.
Go.
LH2.
Go.
Has gas.
Go.
Electrical systems, airborne.
Go.
Ground.
Go.
Facility.
Go.
RFFTS.
Go.
Flight control.
Go.
GCQ.
Go.
Op support.
Go.
COM.
Go.
Umbilicals.
Go.
ECS.
Go.
Redline monitor.
Go.
Quality.
Go.
Op safety manager.
Go.
ULA safety officer.
Go.
Vehicle system engineer.
Go.
Anomaly chief.
Go.
Range coordinator.
Go.
Launch director.
You have permission to launch.
Proceeding with the count. ALC, verify T0 is set for 1030 Zulu.
Verified.
Polling is
ABE, issue
complete
MRT.
and the team is go for launch. From T-minus 7 minutes until liftoff, you'll hear Dylan Rice and the team performing the final steps in the countdown procedure. Several critical activities occur in the final minutes before launch, including verifying fuel tank levels and pressures in the booster and Centaur and arming the flight termination system. At T-minus 1 minute, the Range Operations Commander confirms the range is in a green condition for launch. At T-minus 25 seconds, you'll hear Go Vulcan, Go Centaur, Go Cert2. This is the final status check of the rocket and payload readiness. At T-minus 6 seconds, initiation of the launch pad water deluge system occurs. At T-minus 3 minutes, the main engines ignite. Then after seeing Vulcan lift off from Slick 41, you'll begin hearing flight commentator Hannah Peters providing launch vehicle ascent data.
Has gas, establish scan pattern 71.
Roger.
All steps complete prior to terminal count.
This is Vulcan Mission Control at T-minus 7 minutes and holding. We anticipate releasing the hold in just a few moments.
On my mark, the time will be T-minus 7 minutes and counting. 3, 2, 1, mark. 6:55.
The countdown clock is resumed and we are go for launch at 6:30 a.m. Eastern. After liftoff, ULA's Vulcan rocket will head southeast from Space Launch Complex 41. Here's a look at today's ascent.
Following final confirmation of rocket readiness, twin BE-4 engines and 2 GEM 63XL solid rocket boosters produce more than 1.8 million pounds of thrust to lift ULA's Vulcan rocket away from Cape Canaveral Space Launch Complex 41. Shortly after liftoff, the rocket begins a pitch over to attain the proper flight path. while minimizing the dynamic pressure it experiences during flight. Vulcan then reaches Mach 1, the speed of sound. With the ability to add 2, 4, or 6 solid rocket boosters, or SRBs, Vulcan can be precisely configured to take any mission to space, from low Earth orbit to Pluto and beyond. These boosters augment the rocket's total thrust at liftoff, adding approximately 460,000 pounds of thrust per SRB. With their propellant expired approximately 90 seconds into ascent, the SRBs burn out, followed by jettison. Jettison time is variable, occurring between 100 and 150 seconds after liftoff, depending on mission requirements. Vulcan's guidance system then activates to steer towards the precise target in space. First stage flight continues as the rocket crosses the Kármán line, entering space. With the majority of propellant expended as Vulcan fights against the force of gravity, the BE-4 engines shut down, and the booster stage separates. With the rocket now weighing less than 10% of what it did at liftoff, dual RL-10C engines on ULA's Centaur upper stage ignite. Spacecraft are encapsulated inside a 5.4-meter diameter payload fairing, which provides a protective environment during ascent. Following Centaur engine ignition, the payload fairing is jettisoned. With the first burn complete, the Centaur engine shuts down for a coast phase. Further into flight, Centaur ignites for a second burn, powering the vehicle into a hyperbolic injection orbit. Following the second main engine cutoff, ULA Centaur will continue into an orbit around the Sun.
Port 10.
LH conditioning complete.
.330.
Hydraulics at pre-launch.
This is Vulcan Mission Control at T-minus 3 minutes and 22 seconds. Following liftoff, viewers watching in Florida may be able to see Vulcan in flight as it heads east. To get a closer look at this map, check out ULA Launch on social media. T-minus 2 minutes. The launch vehicle, ground systems, and eastern range are go for launch. For those of you just joining us, I'm Andrea Lenhoff, your host for today's live coverage of ULA's second Vulcan rocket launch. At this time, the team is not working any issues, and we're proceeding towards an on-time liftoff at 6:30 a.m. Eastern.
Clocks have stopped at T-minus 1 minute, 51 seconds.
LC, this is flight control.
Go.
Flight control is ready to reset the clock to T-7 and holding.
Roger. ALC, reset the countdown clock to T-7 minutes and holding.
Roger.
LC, Peony-2.
Go, Peony-2.
Centaur LH2 and LO2 tank venting in progress.
Roger.
LC, Peony-1.
Go.
Vulcan tank pressures are stable.
Roger.
LC countdown clock is reset to T-7 minutes and holding.
Roger.
LC, this is flight control.
Go.
Step 50 SS VAPS and active SCS in pre-flight mode.
Roger.
This is Vulcan Mission Control. The team has reset the clock to T-7 minutes and holding. We are waiting for more information on an updated T0.
LC, Peony-2.
Go.
Centaur tank pressures are stable.
Roger. OSM, place SRB ignition SNA switch to disabled position.
SRB ignition disabled.
All stations recycle systems back to T-7 and holding configuration. Hold occurred at T-1 minute 51 seconds. Report status at completion. Airborne electrical LC.
Go ahead.
Transfer transmitter battery external.
Roger.
LC, Peony-1.
Go.
First step 260, substep alpha, Peony-1, Vulcan pneumatics pressure stable.
Roger.
LC, Peony-2.
Go.
Step 260, substep Foxtrot, CEC active.
Roger.
And substep Golf, sensor pneumatic system stable.
Roger.
LC, prop 1.
Go.
First step 260, substep Delta and Echo, Vulcan propulsion and hydraulic system stable.
Roger.
LC, ECS.
Go.
Step 260, substep Oscar, ECS set point stable.
Roger.
LCSYS.
Go.
Step 260, substep Mike, GC3 ready.
Roger.
LC, fuel 2.
Go.
First substep Juliet, Centaur LH2, continuing topping.
Roger.
LC, Airport Electrical,
This LC.
step 260, subset Papa, Airport Electrical ready.
Roger.
LC, Lux 1.
Go Lux 1.
Vulcan LO2, continuing topping.
Roger.
LC, this flight control.
Go flight control.
Substep Lima, flight control ready.
Roger.
LC has gas.
Go ahead, guys.
For substep India, has gas ready.
Roger.
LC, fuel 1.
Go.
Step 260, substep Charlie, Vulcan LNG, continuing topping.
Roger.
LC, ROM.
Go.
Op 100, step 260, substep November, complete.
Roger.
This is Vulcan Mission Control at T-minus 7 minutes and holding. While we await a new T0, RS rocket ship, ULA's specially designed cargo ship, delivers our rockets to our launch sites in California and Florida. Let's take a look at this unique capability.
Hi, I'm John, captain of ULA's rocket ship. Recently, our travels took us from Decatur, Alabama, to Cape Canaveral, Florida, where we picked up more cargo, and then our final destination was Vandenberg Air Force Base in California via the Panama Canal. The rocket ship, nestled 298 miles up the Tennessee River, takes on the Delta Heavy rocket for United Launch Alliance. The trip begins at an elevation of 556 feet above sea level 23 miles below Decatur is Joe Wheeler Lock and Dam. It is our first of 4 locks operated by the Tennessee Valley Authority on the Tennessee River that allows a step-down staircase of 48 feet in level. Now into the Wilson Pool, we transited approximately 2 hours to enter the Wilson Lock Chamber, the highest single lift east of the Rockies. Once secured in Wilson Lock, we were now lowered a distance of approximately 90 feet. Exiting Wilson Lock and Dam is a narrow channel for 5 miles that leads us generally shallow water past Florence, Alabama. Now passing Florence, Alabama, the rocket ship transits a shallow region with a rocky bottom. The crew expects 5 more hours of transit to Pickwick Lock and Dam. This trip, the vessel anchored above Pickwick Lock for daylight transit-only requirements through the lock. This was due to higher than average water and fast current conditions. At morning twilight, the ship approaches Pickwick Lock. The vessel will be lowered approximately 48 feet, and the transit continues in a narrow stretch of the Tennessee River for 106 miles, commonly referred to as the Wiggles. After passing New Johnsonville, Tennessee, the vessel enters the region known as the Land of Lakes, commonly known to the crew to be more relaxed in a buoy channel leading to the Kentucky Lock and Dam. This elevation drop is approximately 43 feet. After locking and a transit of 21 miles, we leave the Tennessee River in our rearview mirror and join the Ohio River. The vessel now is located in Paducah, Kentucky at an elevation of 320 feet above sea level. The deck crew returns to normal sea watches since the portion of the trip will transit over the lock and dam at Olmsted by a buoy navigable channel. After 5 hours of transit on the Ohio River, the vessel turns southbound on the lower Mississippi River, approximately 14 hours away from Memphis, Tennessee, and approximately 2 days from Baton Rouge. Other major cities along the route are Greenville, Mississippi, Vicksburg, Mississippi, Natchez, Mississippi, and finally arriving at Baton Rouge, Louisiana. There we anchor for fuel replenishment. We now have accumulated 1,070 miles of river and dropped in sea level of a distance of 546 feet to nearly join sea level. Passing New Orleans by night is an impressive sight of lights from the water's edge to the tall office buildings to include the twin bridges known as the Crescent City Connection. The Federal pilot disembarks at the Southwest Pass Sea Buoy as the journey continues to Cape Canaveral. After crossing the Gulf of Mexico, traffic conditions are generally light. At Dry Tortugas, the southernmost point in the continental United States, the ship joins the Florida Straits and follows the Florida Keys to the Atlantic seaboard. The rocket ship finally arrives at Cape Canaveral, completing a sea voyage taking 3.5 days and approximately 8.5 days from Decatur, Alabama. Departing the dock, the journey to sea is a short 7 miles. The pilot disembarks and the transit continues for slightly more than 3 days. We begin approaching Gatun Lock with a complement of Panamanian linemen. Gatun, the first lock, has 3 chambers. Next is Pedro Miguel Lock with 1 chamber, and last, Miraflores Lock has 2 chambers. Signing out with the authorities at Flamenco Single Station, the ship enters briefly into the Gulf of Panama and enters the Pacific Ocean with 12 days of voyage ahead. The crew maintains bridge watch activity, engine room assignments as the deck crew participates in lookout duties and chasing rust spots with paint. The galley crew maintains the morale with 3 square meals daily. Knowing we are close to our destination, the mountains of Southern California finally come into view. A timed arrival and the first landing at Vandenberg Air Force Base commenced at morning break of first light. The first CBC Delta rocket was offloaded with an associated second stage container. The ship can only stay in this small harbor for a window of usually 3 to 4 hours. This is due to tide height constraints and available water to float the ship safely. With more cargo to offload, the vessel anchors nearby east of Government Point to wait for the next available window for an acceptable tide cycle. The second docking at Vandenberg shows the second CBC Delta rocket was offloaded with a fairing section. At this point, in viewing the final delivery of the rocket components, the crew of the rocket ship breathes a sigh of relief, knowing the safe delivery and the critical mission is now complete.
This is Vulcan Mission Control at T-minus 7 minutes and holding. As we await a new T0, let's check back in with Arlena Moses to get another weather update.
Thank you, Edra. Taking a look at radar here this morning, we've had a few more showers develop here across the Gulf Stream, which is located about 20 miles offshore, but they continue to be low enough topped that we're not expecting any significant launch weather concerns. Though, as we continue to push into the window, they will approach the coast. Generally, when we get within 10 nautical miles, which is that white circle that we look at, we have to see them get a little colder topped. A little taller tops, usually about in the 15, maybe 20,000 foot range. And right now, they're kind of below that, so not continuing to be a launch weather concern. So if we go to our forecast, still looking pretty similar for what we were seeing earlier this morning. Overall probability of violations, very low, 5%. Continuing with our breezy easterly winds with temperatures in the low 80s and no significant launch weather concerns. Back to you, Andrea.
LC1 AC.
Go AC.
I have a recommendation for you for R11 line item adjustment.
Proceed.
Okay, we want to take the following 8 line items from a value of 31.1 to 32. These line items are 188, 191, 194, 197, 207, 210, 213, 216.
All right, I copy line items 188, 191, 194, 197, 207, 210, 213, and 216. All those are currently set to a value of 31.1. The new value of 32 is the direction.
Affirmative.
RLM, LC?
RLM, go.
And did you copy the recommendation from the team?
Yes, I did, and ready to implement.
Roger, please put that in work and report when complete.
Copy.
This is Vulcan Mission Control at T-minus 7 minutes and holding. As we look at this beautiful sunrise over Slick 41, we continue to wait on a new T0. Reminder that our launch window today extends to 9 a.m. Eastern. The team continues to work on a new T0, which we will share with you when it becomes available.
LC, RLM.
Go.
Limits changed on 8 requested line items to upper from 31.1 to 32.0.
Roger.
CN1 AC.
Go.
Ready to provide you a recommendation.
LD Net 1.
LD.
Proceed AC.
Okay, the team has reviewed the hold that was put into place and isolated that to the VCU line items. We have adjusted the 8 line items affected by this voltage concern. We have no other concerns with proceeding and are recommending another attempt.
LC concurs. LD.
LD concurs.
And go ahead, LD.
LC, let's please coordinate and implement a new T0 of 11:25:0:00 Zulu.
Roger. RC, LC Net 1.
RC, go ahead.
Please coordinate a new T0 of 11:25:00 Zulu.
Roger.
ALC, please set the countdown clock for a new T0 of 11:25:00 Zulu.
Roger, and work.
And all personnel on Net 1, this is the LC. We're going to reestablish an L25 configuration and proceed again toward another terminal count run. PNE2, LC.
Good.
Initiate CUC airborne pre-chill.
Roger. LC, RC.
Go.
The range has approved our new T0 of 11:25 Zulu.
Roger.
And LC, ALC, countdown clock has been set for new T0 of 11:25. We're currently at L25 and counting.
Roger. LOX 2, LC.
LOX 2.
Perform Centaur LO2 fill and drain valve cycle test.
Roger.
Field 2, LC.
Go ahead.
Perform Centaur LH2 fill and drain valve cycle test.
Roger.
As gas, establish scan patterns 62 and 63.
Roger.
This is Vulcan Mission Control at T-minus 7 minutes and holding. As you just heard, a new T0 has been established at 7:25 a.m. Eastern.
L minus 24 minutes.
Roger. Resume Centaur LO2 topping at flight level.
Roger.
This is Vulcan Mission Control at T-minus 7 minutes and holding. ULA also launches Atlas rockets here in Cape Canaveral, Florida. Let's take a look around.
With spacecraft launched to every planet in the solar system, in addition to critical national security, science, weather, commercial, and human space missions, ULA has a long-standing industry reputation for reliability and orbit accuracy. At our launch site in Cape Canaveral, Florida, the story begins with ULA's Atlas and Vulcan rockets arriving on the RS rocket ship. Rocket ship is a specially designed cargo ship used to transport rockets from ULA's more than 2 million square foot production campus in Decatur, Alabama. Once rocket ship arrives at Port Canaveral, the team offloads and transports the rocket to the pad. Launch site processing begins with Launch Vehicle on Stand, or LVOS. The 107-foot Atlas V boosters and 109-foot Vulcan boosters are transported and hoisted into a vertical position using a crane. Atlas is lifted onto the mobile launch platform, while Vulcan is lifted onto the Vulcan launch platform. With the boosters in place on the launch platforms, solid rocket boosters are added next, followed by stacking of the interstage adapter and Centaur second stage. Meanwhile, the ULA team works simultaneously to help the customer encapsulate their payload into the rocket's payload fairing. The encapsulated payload fairing is the final piece to be mated to the rocket. With the rocket stack complete, the final launch preps begin. Launch countdowns begin with moving the launch platform from the VIV to the pad. Weighing in at about 2 million pounds, the launch platform supports the rocket and contains air conditioning, electrical, and commodities, while the undercarriages bear the weight of the launch platform and rocket. Leading the move are vans providing communication and support to the spacecraft and rocket. Trackmobiles at the rear power the convoy, which also includes an environmental control system providing air conditioning to the payload and rocket, as well as a backup generator. On launch day, more than 24 engineers and managers are polled for system status and readiness to proceed.
Status check to proceed with terminal count.
This is the final status check before launch of all Atlas and Vulcan vehicle systems, ground systems, the spacecraft, and the U.S. Space Force Eastern Range.
Umbilicals. Go. ECS.
The vehicle
Go.
system readiness
Redline
poll
loader.
includes electrical
Go.
systems,
Quality.
hydraulics,
Go.
pneumatics,
Up safety.
propulsion systems,
Go.
flight control,
Relay
and propellants.
Go.
If the rocket is ready for flight and the weather is within the launch commit criteria, polling is completed and the team gives the go for launch.
Status check. Go Vulcan.
Go Centaur.
Go Atlas.
Go Centaur.
5, 4, 3, 2, 1.
Main engines and solid rocket boosters ignite to lift the rocket off the pad.
We have ignition.
Shortly after liftoff, the rocket begins a pitchover to attain the proper flight path, minimizing the dynamic pressure the vehicle experiences during flight. Within the first few minutes of flight, the vehicle reaches Mach 1, the speed of sound, followed by jettison of the solid rocket boosters. Minutes later, propellant levels deplete and the booster engine shuts down, followed by release of the booster stage. At various times in flight, depending on the mission, the vehicle jettisons its payload fairing. From there, the Centaur second stage carries the spacecraft towards its destination with planned engine starts and stops. Finally, Centaur releases the spacecraft in its target orbit to continue its journey.
L minus 16 minutes.
This is Vulcan Mission Control at T-minus 7 minutes and holding. As we move toward a target T0 of 7:25 a.m. Eastern for CERT 2, earlier this year we launched the inaugural flight of the Vulcan rocket. Let's take a look back on that spectacular flight.
Status check. Proceed with terminal count. Vulcan systems. Propulsion.
Go.
Hydraulics.
Go.
Pneumatics.
Go.
LNG.
Go.
LO2.
Go.
Water.
Go.
Centaur systems. Propulsion.
Go.
Pneumatics.
Go.
LO2.
Go.
LH2.
Go.
Pass gas.
Go.
Op safety manager.
Go.
ULA safety officer.
Go.
Vehicle systems engineer.
Go.
Anomaly chief. Go. Range coordinator.
Clear to proceed.
Launch director.
You have permission to launch.
We have ignition. And liftoff of the first United Launch Alliance Vulcan rocket, launching a new era in spaceflight to the moon and beyond.
And the vehicle has cleared the tower. Separation of both SRBs. We have Vulcan Centaur separation. Everything's looking good. Ignition, full thrust. Both engines are up and running. Cut off.
LC Prop 1.
Go.
G&G Snapper Purge cycle test complete.
Roger.
L minus 13 minutes.
Flight control. Perform launch on time verification.
Roger.
OSM. Place SRB ignition SNA switch in the enable position.
SRB ignition enabled.
Verify the FCO, ROC, and OSM hold fire switches are in the proceed position.
Ready to proceed.
RC. Verify solar radiation acceptable for launch.
Verified.
PNE1. Verify post liftoff launch head umbilical purges configured for launch.
Verified.
Launch on time verified.
Roger.
L minus 12 minutes.
Terminal count briefing. If a condition exceeds a launch constraint, anytime after the terminal count status check, the observer shall announce hold, hold, hold on channel 1, identify their station, and briefly state the reason for the hold. RLM. Verify red line monitor and event table in the correct configuration for terminal count.
Verified.
LC LOX 2.
Go.
Centaur LO2 at flight level.
Roger.
LC Fuel 2.
Go.
Centaur LH2 at flight level.
Roger. LC switch is ready. All steps are complete prior to the status check.
Out minus 11 minutes.
We remain in the hold as we continue towards liftoff. In a few moments, launch conductor Dylan Rice will pull the launch team for the final go to pick up the count. 29 engineers and managers are pulled for system status and readiness to proceed. This is the final status check for all Vulcan vehicle systems, ground systems, and the U.S. Space Force Eastern Range. The vehicle system readiness poll includes electrical systems, hydraulics, pneumatics, propulsion systems, flight control, and propellants. Let's listen in as Dylan Rice performs the final polling.
Status check to proceed with terminal count, Vulcan systems, propulsion,
Go.
hydraulics,
Go.
pneumatics,
Go.
LNG,
Go.
LO2,
Go.
water,
Go.
Centaur systems, propulsion,
Go.
pneumatics,
Go.
LO2,
Go.
LH2,
Go.
HASGAS,
Go.
electrical systems, airborne,
Go.
ground,
Go.
facility,
Go.
RFFTS,
Go.
flight control,
Go.
CCQ,
Go.
op support,
Go.
comm,
Go.
umbilicals,
Go.
ECS,
Go.
red line monitor,
Go.
quality,
Go.
op safety manager,
Go.
ULA safety officer,
Go.
vehicle system engineer,
Go.
anomaly chief,
Go.
range coordinator,
Go.
launch director.
You have permission to launch.
Proceeding with the count. ALC, verify T0 is set for 112500 Zulu.
Verified.
ABE, issue MRTU sync pulse.
Roger.
Secure transmitter battery heater and transfer battery internal.
Polling is complete and the team is go for launch. From T-minus 7 minutes until liftoff, you'll hear Dylan Rice and the team performing the final steps in the countdown procedure. Several critical activities occur in the final minutes before launch, including verifying fuel tank levels and pressures in the booster and Centaur and arming the flight termination system. At T-minus 1 minute, the Range Operations Commander confirms the range is in a green condition for launch. At T-minus 25 seconds, you'll hear Go Vulcan, Go Centaur, Go Cert-2. This is the final status check of the rocket and payload readiness. At T-minus 6 seconds, initiation of the launch pad water deluge system occurs. At T-minus 3 seconds, the main engines ignite. Then after seeing Vulcan lift off from Slick 41, you'll begin hearing flight commentator Hannah Peters providing launch vehicle ascent data.
On my mark, the time will be T-minus 7 minutes and counting. 3, 2, 1, mark. 6:55. Ground pyros enabled.
The countdown clock is resumed and we are go for launch at 7:25 a.m. Eastern.
551. Securing Centaur LO2.
Securing Centaur LH2.
This is Vulcan Mission Control at T-minus 5 minutes and 27 seconds. As a reminder, following liftoff, viewers watching in Florida may be able to see Vulcan in flight as it heads east. To get a closer look at this map, check out @ULA Launch on social media.
$459. Securing Vulcan LNG.
Securing Vulcan LO2.
$410. Foliage conditioning complete. $330.
Hydraulics at pre-launch.
$249. FTS at Turtle. $238. $230. CLO2 POP started.
T-minus 2 minutes. The launch
59.
vehicle, ground systems, and eastern range are go for launch. For those of you who are just joining us, I'm Andrew Linhoff, your host for today's live coverage of ULA's second Vulcan rocket launch. At this time, the team is not working any issues, and we're proceeding towards a liftoff time at 7:25 a.m. Eastern.
135. FTSR. $120. SCS count started. $115.
ECS, reduce ECS for launch.
Roger.
T-minus 1 minute.
Rock, report range status.
Range green. .
45. Vulcan tanks at step 3.
BE4 start box go.
28.
Verify ECS reduced for launch.
Verified.
Status check.
Go Vulcan.
Go Centaur.
Go Cert 2.
15.
T minus 10, 9, 8, 7, 6, 5, 4, 3. We have engine ignition. 1. And liftoff of the United Launch Alliance Vulcan rocket, carrying ULA's legacy of reliability, orbital accuracy, and high energy performance.
Everything looking up. BE4 performing as expected. All temperatures and pressures looking good. Vehicle has begun its pitch and raw program. We have 2 good BE4s.
You are hearing Hannah Peters providing launch vehicle ascent data.
And we've ended the pitch program. Vulcan's now at 1.5 or 0.5 Mach. The BE4 is now throttling down in preparation for SRB burnout. And vehicle is past Mach 1, Vulcan is supersonic, and maximum dynamic pressure. Coming up on SRB burnout. And we have indication of SRB burnout. Up next is SRB jettison. Body rates continue to look nominal, trending towards 0. BE4 is now throttling down, and we have SRB jettison. Vulcan is 19 miles in altitude.
We just heard confirmation of solid rocket booster jettison. We have about 3 minutes until we reach our next mission event, booster engine cutoff.
On RCS valve activation. Body rates continue to look good. And we're now just about 2 minutes to nominal BECO. And we've had RCS valve activation. Vehicle continues to look good. BE4s are performing as expected. Body rates are trending towards 0. And vehicles continuing down the range track, traveling currently at 4,600 miles per hour. Continue to have 2 good engines. Body rates trending towards 0. And we're now about 1 minute to nominal BECO. Vulcan is now 1/4 of its liftoff weight. And Vulcan is now passing the Kármán line. And we've started boost phase chill down on the second stage engine. And the BE4s are throttling to maintain a constant acceleration. And we've concluded our boost phase chill now. And PU has gone to open loop. And we have BECO, booster engine cutoff. And we have Vulcan Centaur separation. And pre-start on LH2 and LO2. And we have full thrust on the RL10. And bearing jettison has been indicated. And we've begun thermal loop conditioning on the RCS. And fixed angles on Centaur PU. Vehicle is now 123 miles in altitude, 345 miles downrange, and traveling at 10,000 miles per hour. And we're getting indications that booster performance was within expectations. RL10 continues to perform nominally. And we are partway through a 10.5-minute burn.
This is Vulcan Mission Control at T plus 6 minutes and 20 seconds. We just heard flight commentator Hannah Peters confirm the successful completion of the early phase of today's flight, and all systems continue to operate nominally. Our next event, main engine cutoff, will occur in approximately 10 minutes. While we wait, I'm now joined by ULA's Space Force Program Manager, Megan Lapine. Megan, thank you so much for being here today.
Thanks for having me, Andrea.
I think we're all really excited that we just saw Vulcan launch for the second time. I know a lot is going on with us this morning, but why don't you tell me what's going through your head right now?
Sure. So I think it was a beautiful liftoff this morning. I think we're all really excited to see that. It's such a significant launch in terms of our certification and where we're going with Vulcan. So it was just a tremendous accomplishment from this team. Really proud to be part of the team that did this. Not just the ULA team, but also our Space Force partners, our suppliers across the country. So many people put in so much hard work, so much effort, so much dedication into this, and it's an amazing thing to see this morning.
You never think about it, but there's so many different parts that go into a successful, even just getting off the pad.
Absolutely,
launch.
Yeah.
So why don't you tell us a little bit about the countdown?
Sure. So it was a fairly quiet count to begin with. The team did have to work through a couple of items kind of at the end, which is why we have a window that we worked into. So the team is very experienced. The launch ops team here, the engineering team in Denver, very experienced and really able to, they have a good understanding of the vehicle systems, the ground systems, and we're able to kind of disposition those items and move forward. And we worked a little bit into that window and then got a nice sunrise launch. So
it was really
pretty.
Beautiful. I didn't hate seeing the sunrise. No. Not at all.
That was nice.
So we've talked a lot during the broadcast about how this is really important for certification, this launch today, and our government customers. Why don't you tell us a little bit about that?
Sure. Actually, before the launch today, we had a chance to talk to our colleague, Greg Novi. He put together a little description of how we get new launch vehicles certified for national security space. So why don't we take a look at that, and then we'll talk some more.
Great. Let's take a look.
In 2011, the Air Force, the NRO, and NASA got together and created a guide for new entrants to be able to come into our marketplace and launch national security missions. Even though Atlas and Delta have flown successfully, the Vulcan vehicle, which took the best of the best from both sides, is substantially different enough that it requires us to go through this certification process to be able to fly national security missions. ULA's certification plan is categorized as a Category 3 alternate 4, which requires 2 certification flights and customer insight into our processes and analysis as we go forward. The process involves kind of 3 phases: the assessment phase, the evaluation phase, and the certification phase. We're currently in the certification phase right now. We've completed over 5,000 verification records, or verifications that show how we are designed, how we are analyzed, and really backed up by test reports and through all the non-recurring development and qualification effort that has taken place over the last few years. In addition to that, we've completed over 150 component level tests and over 27 system level tests, huge tests that take a look at the complete element and put it through its rigors to be able to show it's good for flight. An example of qualification, at the component level is the valves, where we are qualifying them to new vibration, dynamics, those kind of tests at the component level, where our systems testing is more at the element level, the booster, the Centaur V, the payload accommodations, where we're going through structural qual and frequency ID testing, acoustic testing, to really show the durability of those vehicles and those elements. After today's mission is complete, we will give the customer the quick look data in about 2 weeks, and then follow up with any questions that they have on any kind of the analysis, and kind of really validate our predictions for flight and support them in their chief engineering review boards that lets them go system by system and make a recommendation to their leadership on our certification going forward. One of the key items for success of getting through our certification plan is the working relationship we have with the customer. We meet with them on a weekly, daily basis as required. We're shoulder to shoulder with them in the factory, with our suppliers, in our design rooms, and it's really helped be able to get the message across that we're in this together. I'm really looking forward to the certification process being complete. And here with this cert flight, we're going to get the data to the customer, help them wrap up any loose items they have, and be in a great position to fly national security missions going forward.
That was a great video. So following up a little bit about what Greg is saying, why don't you tell us a little bit about how ULA has been working with the Space Force to certify Vulcan?
Sure. So as Greg mentioned, we've been working shoulder to shoulder throughout the entire design, development, test, build, and now operations for Vulcan with the Space Force. So they've been our partner throughout that process, and we continue to provide information, share data. And then with this flight, once we complete the mission today, we will provide them that data and then continue to support their certification efforts.
Great, that's very exciting. So, you work with the Space Force pretty regularly, obviously.
Yes.
But what's next for the Space Force and ULA, and how is Vulcan a difference maker for the Space Force?
Sure. So once we get certification completed, that will allow us to be able to launch the national security space missions that we have on contract. So we have some, that we're getting close to being ready to launch, and we're really excited to focus on those and the mission success for those missions. And Vulcan generally was designed to meet the entire range of the national security space requirements. So it has the Centaur V upper stage. It's the highest performing stage in the world. And that's really a difference maker in terms of being able to meet those most critical orbit requirements, the most stringent accuracy requirements, the most challenging orbits, delivering the spacecraft to where they need to be when they need to be there. And that's important as we continue to partner with our customer as their requirements evolve, will evolve, and be able to deliver the capabilities they need. And we're looking forward to building that partnership and continuing it.
Great. I'm super excited for the future with Vulcan and the Space Force.
Me too.
Thank you so much for joining us, Megan.
Thanks,
I'll let
Andrea.
you get back to console.
All right.
Thank you so much.
Thanks.
Just about 2 minutes to MECO, or to nominal MECO. Everything continues to perform nominally. The vehicle is now traveling at 14,500 miles per hour. And we're now approaching approximately 1 minute to nominal MECO. Everything continues to look good. Our Alton engine parameters are as expected. MPU is correcting as expected. And PU has come off its lock stop.
This is Vulcan Mission Control at T plus 15 minutes and 35 seconds. We're approaching the first main engine cutoff. Let's listen in.
Car is now orbital. And PU has gone to open loop. Coming up on MECO. And we have MECO, main engine cutoff 1.
This is Vulcan Mission Control at T plus 16 minutes and 22 seconds. We just heard flight commentator Hannah Peters confirm the successful cutoff of the main engine and all systems continue to operate nominally. Our next mission event, main engine start, will occur in about 15 minutes. While we wait, let's hear more about the Vulcan rocket from Mark Peller, ULA's Senior Vice President of Vulcan Development and Advanced Programs.
Cert 2 is the final step in formal certification of the Vulcan rocket. After launch today, we'll take the time to go through the data, verify the system's performance, and move on with our government customer to complete the formal certification. And the real exciting part for me is really turning the corner and getting to start to perform those missions. I know we have a really busy manifest with some extremely important missions for this nation, and I'm just so excited to have the opportunity to support those and really start to realize the promise of Vulcan and everything that we've worked so hard on for the last 10 years and the capabilities that it will bring and the missions that it will support for our country. This is the start of a new era with Vulcan. We're very excited to turn this corner and move into the operational phase of the Vulcan program. Vulcan right now is capable of launching a variety of missions, from low Earth orbit to direct inject to geostationary orbit 23,000 miles above the Earth, to launching to the moon or elsewhere in our solar system. Certification implies it's determined to be ready by the US government to fly the most critical national security space missions. There's a whole range of missions, from low Earth orbit to some extremely challenging orbital injections, direct inject to geostationary, and so forth. So Vulcan will be not just capable, but certified to fly that full range of missions. Cert 1 was extremely successful. We obviously went into it with high confidence after all the work that had gone into preparing for the launch, but it still greatly exceeded our expectations. And we set the bar very high for ourselves. We picked a very complex orbit to inject into. We launched a payload on a modified trajectory to the moon. Really unique for a first mission to do something so challenging. We did that very successfully. After we sent the payload on the way to the moon, we decided to continue demonstrating the capabilities of Centaur. So we did a planned coast, another burn of Centaur, and eventually we put the Centaur upper stage into a heliocentric orbit. We set the bar very high for ourselves, and the system worked flawlessly. We gave the payload a very smooth ride and very precise orbital injection, and met all of our other objectives for demonstrating the capability of Vulcan and Centaur. Yeah, Vulcan has been extremely successful. Coming into first launch, we already had a backlog of over 70 missions, which is unheard of in this industry. And that's really a testament to the capabilities of Vulcan, the value that we provide, and the reliability. Versatility, value, and reliability, those are what really distinguish Vulcan. Versatility in that Vulcan, in how we can adjust the basic configuration, can fly without compromise to a variety of orbits, from more straightforward injections to low Earth orbit to more complex injections, direct inject, to orbits like geostationary, to the moon and beyond. And that is unique in this business, and it can do it across all of those orbital regimes, providing great value for the customer. And of course, Vulcan brings forward from our Atlas and Delta experience the reliability and precision in terms of orbital accuracy that our customers across all those markets have enjoyed for years.
This is Vulcan Mission Control at T plus 20 minutes and 43 seconds. Our next mission event, main engine start, occurs in about 10 minutes. We'll take a brief break in live commentary while we wait for that event. During the break, you'll continue to see the live flight animation powered by telemetry from the rocket as it makes its way to orbit. See you in about 5 minutes.
And we've now secured power on our GPS transmitter and receiver. And we're now venting down on the LO2 and LH2 tanks. Vehicle continues to perform nominally in its PTC role. RCS firing as expected. And the vehicle has begun its turn to its MES-2 attitude. And Centaur has now begun to despin from its PTC roll in preparation for MES-2.
Welcome back. Thank you for following mission progress of ULA's Vulcan Cert-2 flight. If you're just tuning in, I'm Andrea Lenhoff, joining you from ULA's Advanced Spaceflight Operations Center at Cape Canaveral Space Force Station in Florida. ULA's second Vulcan rocket lifted off at 7:25 a.m. and all systems continue to operate nominally. As we continue in second stage flight, let's hear from ULA's Director of Upgrades Development, Amanda Bicchetti, about the capability of ULA's venerable Centaur.
Centaur, the second stage for ULA's Vulcan rocket, was developed in the 1960s and continues to play a vital role in our nation's efforts in space. Vulcan lifts off with the booster vehicle powering the vehicle up into space. We then separate the Centaur second stage where it takes the spacecraft where it needs to go. Second stage of flight is so incredibly critical as that is the stage that takes the spacecraft to its final orbit and ensures that it is exactly where it wants to be in the orientation that it wants to be. Centaur is the most efficient stage that exists. That is what sets it apart in the industry, and it's largely based around two key design features. The first being that it is a pressure stabilized stage utilizing stainless steel that is so thin it's about as thick as a dime. That, coupled with the fact that we utilize cryogenic fluids, both liquid hydrogen and liquid oxygen for our propellants that fuel the RL-10, that allows it to be the most mass efficient stage that is on the market. The Centaur variant for Vulcan, the biggest piece that you'll notice right off the bat, it is significantly larger. Essentially, we took the Atlas 3.1 meter diameter vehicle and we stretched it to 5.4 meters. That allows us to fill even more propellant with only a tiny mass impact from a dry mass perspective. Additionally, we have now, for all of our standard vehicles going forward, we'll have a dual RL-10 engine configuration. That's 2 times the thrust, 2 times the total impulse. What that means is not only can this stage take our customers to the same orbits we always have, including direct inject geosynchronous orbits, but we can lift more when we do it and we can go even far beyond those orbits. That allows us to ensure that we are supporting not only our warfighters and our nation, but exploring the universe and going where we need to go. The other piece we took advantage of is with the whole new vehicle, we modernized all of our infrastructure. We have all new production tooling in the factory, allowing us to build up Centaurs quicker than ever, and infrastructure at the launch site that can launch them faster than ever. And with all these updates, we are able to significantly increase our rate to support our customer needs across the board. While this is only our second launch for Vulcan, we are well underway with many upgrades for Centaur. In fact, next year we're going to be rolling out what we call our LEO optimized Centaur, which is essentially a shorter version of Centaur, allows us to have the most mass efficient stage when launching to a LEO orbit. But that's just the first of many. We have several on-orbit demonstrations that we have planned. That's going to allow us to test out new capabilities and really test out the art of the possible, including extending the life of Centaur. That long duration capability for Centaur is going to be essential for supporting and protecting our nation.
On the LH2 and LO2 tanks.
This is Vulcan Mission Control at T plus 29 minutes and 49 seconds. We're about a minute away from the second main engine start. Let's go back to Hannah Peters.
And we have pre-start on LH2. And LO2 pre-start. Coming up on main engine start 2. And we have ignition and full thrust on the RL10. And vehicles begun closed loop steering.
This is Vulcan Mission Control at T plus 31 minutes and 20 seconds. We just heard confirmation of second main engine start. While we wait for engine cutoff, scheduled to occur in about 4 minutes, let's take a look at how our Vulcan booster stage is painted prior to departing ULA's Decatur, Alabama factory. This is Vulcan Mission Control at T plus 33 minutes and 23 seconds. We're coming up on the second main engine cutoff in just over a minute. Let's listen in.
Vehicle continues to look good in this burn. Engine parameters are as expected. PU is correcting as anticipated, and our body rates are trending towards 0. Approximately 1 minute to MECO. Approximately 30 seconds to MECO. And we have MECO, main engine cut off too. We're now venting the fuel tank. We have approximately 2 minutes and 49 seconds until simulated spacecraft separation. Full settling on RCS. And the vehicle is now rolling to its simulated SV step attitude. And RCS is now doing 50% settling and thruster warming. Body rates are trending towards 0 now. Coming up on our simulated spacecraft separation. Vehicle is now rolling, and we are depressurizing the LH2 tank. And we have simulated spacecraft separation. We now have an approximately 28-minute coast until the third burn. And vehicle has started its descent and is now pointing towards Cedrus. Passing 40 minutes into flight, Centaur continues to look good throughout this coast period. All parameters are looking nominal. RCS is performing its periodic firing, and our body rates are trending towards 0.
This is Vulcan Mission Control at T plus 41 minutes and 50 seconds. We just heard flight commentator Hannah Peters confirm the successful completion of the beginning of today's flight. This completes today's mission coverage. I am now joined by ULA's CEO and President, Tori Bruno. Tori, thank you so much for being here with me today.
My pleasure.
I've worked on this program for a really long time. I am very excited to see the beautiful launch. I feel like we waited for the perfect moment to lift off. So I just want to say congratulations. It's just an incredible day.
Well, thank you, and you too.
Thank you. And thank you so much for being here. It's my understanding you want to tell us a little bit about today's flight.
Yeah, so the trajectory was nominal throughout. We came to our first insertion on the orbit that we intended, so all of that is good. We did, however, have an observation on SRB number 1, and so we will be off looking into that after the mission is complete. Other than that, the flight was nominal.
And you know, that's the great thing about these certification flights is it allows us to get more information as we get into our regular launch cadence, but you know, just a testament to Centaur and Booster on how beautiful that launch was so far.
It was a gorgeous liftoff, absolutely.
Great. So as we continue on with this launch, after the launch, we'll go through, look at the data and just make sure that we're certified for, you know, national security space missions. Why don't you tell us a little bit about what that certification means for ULA and the launch industry as a whole?
Yeah, certainly. Well, for ULA, we designed this rocket for the national security mission space. In completing the second certification flight successfully allows us to begin those missions that are urgent and important to the country. What it means overall for the industry is that we've introduced a new launch vehicle and a vehicle that is capable of launching at a pretty high tempo, and so we have broadened the entire country's capability for lift, and you will begin to see that launch tempo really tick up, especially next year.
I'm really looking forward to that. Who doesn't like a rocket launch?
Well, no one as far as I know.
I know, those people would be crazy. So I do want to say how hard it's been the past couple of years. Everybody has worked to get to this moment. I mean, this is kind of a pinnacle for us in terms of overall Vulcan development. Do you have anything to say to all of the folks that have worked on Vulcan over the years?
Absolutely. I just want to express my appreciation. Developing a new rocket is a monumental task. It is one of the pinnacles of engineering accomplishment. It truly is rocket science. Yes. Our team has worked so very hard over the last several years to design this rocket, to build it, to test it, to overcome the many technical challenges that are inherent to that. I could not be more proud of our team. Thank you all.
Thank you, seriously. This has been just so incredible to be a part of this team, and I don't think that there's anything I've been as proud of, besides my children, of course, to this moment. So now that we've launched, hopefully we'll get certification under our belts here shortly. What's next for Vulcan?
Well, we have a pair of national security missions in the pipeline. So we'll do those, and then we'll roll into next year with a whole number of flights.
Great. It's going to be an exciting year next year for sure.
Yes, it will.
Well, Tori, I know you have to get back, but thank you so much for joining us today. I am very excited about today's launch, and I always appreciate your time.
Oh, you bet. Thank you. You're doing a great job today.
Thank you so much.
All right.
Thank
Bye-bye.
you. Bye-bye. At this time, we'll end our live coverage. For more information about the Vulcan rocket, please visit ulalaunch.com. I'm Andrea Linhoff. Thank you for joining us on this exciting day. Before we sign off, let's take another look at the Vulcan rocket lifting off the pad. T-minus 10, 9, 8, 7, 6, 5, 4, 3. We have engine ignition. 1. And liftoff of the United Launch Alliance Vulcan rocket, carrying ULA's legacy of reliability, orbital accuracy, and high energy performance.
All temperature